Good afternoon. Welcome to the Science Café, organized by the Faculty of Science of Carleton University. My name is Michel Barbeau, and I'm the director for the School of Computer Science. So this afternoon, we have a talk on 5G drone cellular communications, research and challenges. The talk will be delivered by two speakers. I'm pleased to introduce first Fatemeh Banaeizadeh. She's a PhD candidate in the School of Computer Science. And I'm also pleased to introduce Pravallika Katragunta. She's also a PhD candidate at Carleton University in computer science. They are both experts in 5G and drone communications using 5G. And they are working on machine learning under the supervision of Professor Kranakis, Joaquin Garcia-Alfaro, and I. And they are both MITACS and Ericsson interns since 2020. So over to you, Pravallika and Fatemeh. Just forgot to mention, so we will have a 30 to 40-minute presentations, and after that we will take questions. So over to you, Pravallika and Fatemeh.
Thank you for introducing us, Professor Michel. Today we are going to present on 5G's drone cellular communications, research and challenges. The main topics we would like to introduce today is 5G communication, drones, and the integration of drones in 5G, and what are the challenges we are facing during the integration of drones in 5G, and how we are approaching these challenges by the help of AI. So in general, in radio communication, there are two main components. One is the base station and one is the user. So the communication between the base station and user happens when one of it acts as the receiver, transmitter, and one of it acts as the receiver. This here in this slide, I would like to mainly explain the different types of base stations and also different types of users. The users can be a ground user or drone aerial users, which can, so the ground users can be any mobile phone, IoT devices, vehicular communication, like any mobile device or any user which are communicating from the ground are considered as the ground users. The aerial users can be the drone users, which is same like the ground users, but which are flying in the higher altitudes in the air, and the communication between the base stations and the users, it varies on different channel modeling and communication perspective side. So if there is the different base stations, one is the ground base station, which we can see in the figure. So ground base station is a traditional cell towers, which we see in the outdoor environments, which are highly equipped with the radio equipment to provide service to the users. And there is also other type of base stations which are considered as aerial base stations or tethered aerial base stations, which are used to provide service to the users where there is no reach of connectivity from the traditional ground base stations. And while the communication happening between these components, there are some challenges which will be explained in the further slides. And to overcome these challenges, we have considered AI approaches to overcome those challenges, which will be explained in the further slides. So in this presentation, we will be giving a brief explanation of what is 5G and beyond communications and drones and cellular connectivity. And then we will be discussing about the research challenges. And then we will give a brief introduction on artificial intelligence. And we will briefly explain about our research works in the end. So a lot of people might have this question like why we are using 5G, or what is the importance of 5G, and why not 4G. So I have added this figure to show the main differentiation between the 4G and 5G communications. Before explaining the key capabilities of the 5G and 4G requirements, I would like to give a quick idea on IMT and ITU. ITU is a International Telecommunication Union. It is a community to designate the specifications and standardizations of broadband mobile systems. And like for each generation networks, these specifications are mentioned with the term IMT, which is the International Mobile Telecommunication. So here in this figure, we can see IMT 2020 and IMT Advanced. IMT Advanced is the specification requirements mentioned for the 4G, and IMT 2020 is for the 5G. So here we have 8 key capabilities mentioned in this figure. So these 8 key capabilities are the standard and set of specifications for 4G and 5G networks network. So here we can see the peak data rate, user experience data rate. So what is a data rate? Data rate in general term, the amount of data transferred from one device to other device in a network per second. So here the peak data rate mentions about how much data it is transferring from the transmitter to receiver, and also user experience data rate is the data rate mentioning about how much the user is experiencing, how much the user is receiving the data rate. So we can see the difference here. For the 4G, it is 1 gigabits per second, and for 5G, it is 20 gigabits per second. The same with the user experience data rate. And in each capability, we have the difference of the 4G and 5G specification requirement. Area traffic capacity is mentioning about how many number of devices in a given certain area it is able to cover the device, in certain area. And network energy efficiency is about the amount of power utilized and how much power, how much energy it received from the in the receiver side. We can see the difference in the 4G and 5G here in the figure. And also connection, the other key capability is the connection density. So in a given area, for how many number of devices it can give a quality of, it can provide quality of service in a given area. So here we can see that 10 power 5 devices per kilometer square for 4G, and 10 power 6 devices per kilometer square. And the latency is one of the other key capability. So latency is nothing but a data delay. So when the sender sends a data, how much time, how much delay it is taking to receive the data from the receiver side. So this is one of the main important key capability, which for 4G and 5G we can see. So in 4G, the latency is 10 milliseconds, where in 5G it is 1 millisecond. There is a big difference. There is a 9 millisecond difference in 4G and 5G latency. And mobility is one of the other key capability, where any vehicular related communication, like any vehicle or drone, which are like flying in a certain speed, how much more, like with how much speed and mobility when they are traveling, they are having a proper quality of service. So if we see here for 5G, it is 500 kilometers per hour. With the more mobility, still it is able to get proper quality of service, where in 4G it's 400 kilometers per hour, 350 kilometers per hour. So there is a difference, like how the quality is differentiated between the mobility also. And the spectral efficiency is one of the other key capability. So spectral efficiency or bandwidth efficiency is the amount of data transferred in a given amount of time from sender to receiver. So if we see here 8 different capabilities, for each capability, we can see that 5G is providing better service than 4G in many key capabilities. So now, so we in general, we have different use cases. For example, there is a big stadium with different people, too many people. And here the main purpose is to provide a better connectivity and connectivity than the latency. So there is one other use case where there is a surgical operation going on in a remote area, and through telemedicine, when they are taking care of the surgery, there shouldn't be any latency. So depending on the use case, these different key capabilities play a main role, like for which use case which key capability is important. So to differentiate that, in 5G, they have three different use case scenarios. One is the enhanced mobile broadband, and one is the massive machine type communication, and one is the ultra reliable low latency communication. And EMBB, which addresses the human-centric use cases for access to multimedia content, services, and data. We can have example for this use case scenario, like, for example, 3D video and virtual reality, videos monitoring. All these use cases come under this use case scenario. And massive machine type communication, which is MMTC. For this scenario, this scenario is with a large number of connected devices, which are typically transmitting with a low volume of non-delay sensitive data. In this use case scenario, we can have examples like IoT, Internet of Things devices, smart agriculture, smart cities, smart home, remote monitoring. All these examples, all these use cases can come under this category. URLLC, ultra reliable low latency communication. So which has strict requirement for capabilities such as throughput, latency, availability. So under this use case scenario, it's very important and very strictly followed these three, latency, throughput, and availability. So examples under this use case scenario can be autonomous vehicles, remote patient monitoring, telehealth, industrial automation. These can be the examples under this use case scenario. So if you see in the figure, based on the use case scenario, we can see the key capabilities which I have explained previously. We can see the importance of that key capabilities. For example, enhanced mobile broadband. Here, the main key capabilities are peak data rate, area traffic capacity. So in this way, for each use case scenario, the use cases comes under these use case scenarios. I have also added one other figure here to show the different use cases comes under this use case scenario. So like how I previously mentioned, the smart home buildings, voice recognition, smart city, all these comes under massive machine type communication, and enhanced mobile broadband. The main purpose of this use case scenario is to provide better bandwidth. So like we can see that gigabits in a second. So, and also URLLC, this use case scenario, all these use cases we see, industry, automation, mission critical applications, self-driving, all these use cases comes under this category. So now I have given a brief introduction on like what is the importance of 5G than 4G, and related to latency, speed, and connectivity. It is performing more better than the 4G. Now I would like to give a quick introduction on drones and cellular connectivity. So normally you can see in the figure different types of drones. I'm not going hardware perspective of the drones. Here, my focus mainly was from software side, how to connect a drone, because different drones are used in different use cases according to their purpose. So here, like in the drone, in technical term, we mention drone as unmanned aerial vehicle, which is a UAV. So it is a aerial robotics. Drone is one of the aerial robotics which fly at different altitudes. And as we know, we don't need any human pilot on board to fly a drone. We can control the drone remotely or via embedded autonomous computer program. So why we are using drones? So one of the popular use case, most of us know is we use it for filming or monitoring. So a lot of people travel, they try to capture the nature, they try to videograph the sceneries. So for this use case, it's very popular. And apart from that, there are also different use cases where a drone can be used. For example, storm or earthquake. So when this happens, when storm or earthquake happens, the normal cellular infrastructure will be damaged. They can't have proper connectivity. During that time, to know like how the damaged area is like how the damaged area is there and how it is affected, how they can provide any rescue service operations, they can fly a drone, they can send a drone, and they can monitor the affected area. And also good delivery. So for this, I can give a best example, Amazon. Amazon have deliveries all over the world, and delivering through drones is one of their main use case. And also during COVID, drone deliveries were used in many places in remote areas or COVID affected areas, not to have where they cannot send a human. They used drones to send the medicine or regular food supplies, or in different ways they use the drone for delivery. And also the other use case can be agriculture. In agriculture, they can use the drones for monitoring the crop growth, and also for spreading the pesticides. There are different operations where they can use the drones in agriculture. So not only these use cases, there are many use cases in different ways drones are enabled in different perspectives. So I have given a brief introduction on like different use cases on drones, how we are using them, but why we are why it is important to integrate the drones into 5G. So the main importance, as I explained in the key capabilities, so it has the low latency, high bandwidth and throughput, and also secure and reliable communication. So when flying a drone, we have licensed and unlicensed spectrum. So when we have a licensed spectrum under 5G, it provides more secure and reliable communication. And also the latency, as I mentioned before, it has in 5G only 1 millisecond latency. So with that low latency, the drones can be connected all the time, and they don't have to be disconnected or having this delay in data transfer. And also with the high bandwidth and throughput, they can have proper data transfer. And what are the functions of drones in 5G network? So like in previous slides, use case scenarios, I have mentioned different scenarios. So here drone can be considered as a aerial user. It can be considered as a aerial base station and also a relay node. So aerial base station is where there is no proper coverage from the ground base station. It can give a temporary coverage to IoT devices, mobile users, vehicular communication. Depending on the use case, it can provide the connectivity as a base station. And the aerial user, in previous use cases I have mentioned, those use cases, how they use the drone. So a drone can act as a user to monitor and help in different use cases. Relay node is where a drone acts as an intermediary node between the mobile users and the base station to have a proper connectivity. Now I have given a brief introduction on 5G and drones and cellular connectivity, the research challenges and the artificial intelligence solution approaches were discussed by my teammate Fatemeh, and then we will discuss our research works briefly.
Okay, Fatemeh, can you switch the slides to full screen?
Sure. If yeah, I think because Pravallika is going to control the slide, if I wanna, should I share my screen separately here?
It's good now.
Okay, thank you.
Thank you.
Thank you, Pravallika. Hello, everyone. In this part, I will at first explain about some existing challenges which we have for UAVs, because after integrating the UAVs in serial communication, like other new technologies, we have some challenges, and in order to deploy them effectively, we have to address all of these challenges. Here in this slide, I will go through to each of these challenges one by one, and after that I will explain about learning approaches and some of the learning approaches we use to address some of these challenges. These challenges can be interference management, energy consumption, optimal 3D localization, handover, optimal trajectory, and channel modeling. As a brief explanation, I would like to talk about what is the interference. Generally, interference is serial communication is defined as a when two users will send the signal simultaneously to the base station, their signal interfere to each other. This is called interference. When it comes to the UAV, we can explain like this. As we said, UAVs are flying in different altitude. For example, when it's located in location 1 in this altitude, which is shows in these figures, the UAVs are in the coverage range of the several base stations. When it's going to communicate with one base station, which is the main base station for UAV, and UAV will get a service from this base station, not only the main base station, but also the other base station which are located around the main base station will get a signal from the UAV. This signal for other base station is considered as an interference. This also might happen in reverse scenario. For example, when one base station is going to communicate or send the data to their ground users, this UAV will get a signal from different base station at the same time. This signal from base station is considered as an interference, this time for UAV. Usually interference decrease the quality of communication and also attenuate the signal too much. As a result, in order to get a proper result, increase the data rate or maximize the data rate, we have to design some techniques to improve the interference and or to mitigate the interference. The next challenges in for UAVs is energy consumption. As we said, we have different type of drones. Each drone or all of these drones are equipped with a small battery. The battery has limited energy resources. Then when they start their task to do their mission and fly from the initial location to go to the last location, definitely they consume an amount of energy. We have to consider how much energy is used by them, and they also after doing their task, they should have even enough energy to come back again to their main station for recharging again. As a result, we have two challenges here: how to optimize the energy consumption in UAV to increase their flight time, because if we decrease the amount of energy consumption, we can increase also their flight time. The second challenge is how to design an effective energy usage model based on drone types, because drone also, like other devices, they have a small battery. But the existing energy model, which we use, for example, for sensor, like a ground user, we cannot apply for UAVs, because the UAVs are flying in the air in the different direction. They're flying vertically, horizontally, and all going up, down, left, right. Each of these direction will use a different amount of energy. For example, when UAV is going up, the amount of energy which is used is more than going down, because going up, it will be against the gravity. As a result, more energy will be used. So here we have to design one energy model for each type of drone. We cannot apply one energy model to all type of drone also. The second challenge, the third challenges will be the optimal trajectory. For example, And the third challenges will be the optimal trajectory. When a UAV, after taking off from the ground, it will reach one altitude, will be the first location of the UAV. UAV, in order to accomplish its task, it has to reach the terminal location. Between the initial location and terminal location, there are many trajectories, but all of these trajectories don't mean they are a good trajectory, and we have to use these trajectories. Some of these trajectories is not safe for UAV, and it has many obstacles, right? Like high-rise building, wall, trees, and they are not safe for UAV. As a result, we have to design a trajectory to avoid any collision. Or sometimes the trajectory is designed to maximize the data rate for either ground user or UAVs or both of them. When UAV, for example, working as an aerial base station, we have to design a trajectory to improve the coverage area for ground users. And also sometimes we design a different trajectory to decrease the energy consumption. Therefore, the trajectory which is designed for UAV, it should be based on our defined goal to reach our goal during the UAV is flying from the initial location to the terminal location. The next challenge is handover. What's the meaning of handover? Handover meaning switching from one base station to other base station. As we said, UAVs, when they are flying in different altitude, based on their height, they are in the range of different base station. For example, when they are in the first location, they will get service from base station 1. After flying a little and going to the next location, it might get a signal from the other base station. The UAV immediately switch to the other base station to get a service from that base station, because the signal which is getting from the second base station is stronger than the current one. But sometimes this handover is not necessary, and the base station still can get a proper services from the first base station. Here we have to manage to decrease the number of handover, and also decide which time is the best time for UAV to implement the handover. Why handover has negative effect on our communication? Because at first it increased the disconnection, because UAV has to disconnect its connection from the current base station and establish a new connection to the new base station. This disconnection and establishing a new connection increase the delay for the UAV communication. Next step. The last challenges here we are going to talk about, this one is channel modeling for UAVs. For the existing cellular networks, we have different standard channel modeling, but we cannot apply them for the UAVs because of two reasons. For example, for the ground user, the type of channel is different. This channel is ground to ground communication, is defined as a ground user to ground base station. But when it's come to the UAV, the type of channel will be air to ground communication, which is from the UAV to base station, or air to air communication, which is between several base stations which are flying at the same time in the air. And also, the channel modeling for ground users is designed based on two-dimensional area, but UAVs are flying and they operate in a three-dimensional area. And based on their location, they have different channel condition. For example, in the first figures, it shows a figure of urban area. In urban area, as all of us know, we have many obstacles like high-rise building, cars, vehicles, and also walls, trees. As a result, UAV in some location can have a direct connection with base station, but in some altitudes, during the reflecting to some surface, they are not able to have a direct connection with base station. As a result, based on their altitude, the channel condition is also different. But when it's come to the rural area, in rural area, we don't have this many obstacles like urban area. And mostly they will have a line of sight channel communication or direct connection with the base station, which generally the quality of direct connection will be better than the quality of not direct connection, because it will experience attenuation, interference, and reflection from different surface. For improving these challenges, we use artificial intelligence. But here, our main focus are on the first challenge, which is interference management. What is exactly the meaning of artificial intelligence? Artificial intelligence means our goal is to train one agent to perform a task intelligently. In order to train an agent, we are using the machine learning approaches. Machine learning approaches generally categorize into 3 different groups: unsupervised learning, supervised learning, and reinforcement learning. What's the definition of each of them? About the unsupervised learning, we have a huge amount of data. This data doesn't have any label. Agent during the training has to learn the pattern of the data or the distribution of the data. But when it's come to supervised learning, again, we have a huge amount of data, but our data has label. It means when we input some data to our training networks, or it can be a neural network or fully connected neural networks, we know what should be the output. In terms of RL, when it's come to reinforcement learning approaches, we don't have any RL, we don't have any database. The agent directly interact with the environment. Through interaction with environment, it will learn and it will get a feedback. In our research area, we use a reinforcement learning, and we didn't use unsupervised learning or supervised learning because of some reason. At first, collecting the data, reliable data for training the machine learning approaches is really difficult, and sometimes it's not possible. For example, when we are working on medical healthcare area, clinics or hospital, the data confidentiality of their user is really important for them, and they won't release the data for us or for the researcher to do their research and get a result. So if we want to even generate our data, I mean, like a kind by some tools or simulator, the quality of data or the feature of data might not be exactly the same like a real data. And this, the second one, when even we have a database, a large amount of data, this data is only applicable for one environment, and we cannot use this data for different environments, even when they have some similarities, because each environment has their own features and their own maybe distribution and their own differences. Because of this, we use the reinforcement learning approaches here. Now, what is reinforcement learning and how it works? In reinforcement learning groups also, we have many algorithms, but all of them composed of 5 main components: environment, agent, state, action, and rewards. What is the environment? Environment generally is defined as a world of agent. For example, about the autonomous vehicle, the road can be considered as a world for the agent. Agent is it can be an intelligent agent like UAVs or base station or robots, which is able to learn new things or learn some environments by getting the feedback from the environment. A state is defined as a current position of the agent. Each activity which is done by agent is called as an action. This activity causes agent to move to the next location, a next location which is considered as a next state. By doing each action, agent will get a feedback. Feedback is called reward. This feedback can be a good feedback or bad feedback. If agent is getting the good feedback from the environment, it will learn, okay, next time if I was again in this state, I will take this action, because by taking this action, I will get a good reward. But if it was a bad reward, next time I won't repeat this action, I will try other action, because this action will give me the negative reward. Here in this figure shows shows how reinforcement learning works. For example, as I said, we have agent. This agent interact with environment by taking one action, and then after taking the action, it will go to the next position, and it will get a reward from the environment. And this process continue until the end, until agent get a proper knowledge from the whole environment. The main goal for reinforcement learning here is we are going to maximize the return reward. In our approach, in our research, we use one type of reinforcement learning approaches, which is called multi-arm banded or MAB. How the multi-arm banded approach works. This approach is designed based on a slot machine which are in casino. For example, when you want to go casino, we have several slot machine, and we will put money in one of these machine and try our chance by pulling each arm or pulling each slot. If we get a point, then we will decide, okay, this slot is a good slot, and I will try more and more this slot. If by pulling that slot, I will lose the money, then I won't repeat that slot again, because I already lost the money. Through playing with this slot, I will learn which slot will return the best reward for me, and I will get more money. In terms of multi-arm banded also, here, when you want to train the agent by pulling, for example, 10 times or 20 times or even 100 times is not enough for training the agent. And sometimes we have to repeat this 1,000 or 2,000 times. For human, or for us as a human, it will be really difficult to remember the result of all result of gains by pulling all of these slides during the training. As a result, several approaches, several algorithms have been proposed by researchers to follow the process of the training. And by following this process of training, we will realize which of these slots will return the best action for us. Here in this presentation, I will explain just 3 approaches which we use in our research: epsilon greedy, upper confidence bound, and Thompson sampling. But how this algorithm work and will help us to recognize or detect the best action, which is return the highest amount of the reward. Can you go next slide, Pravallika? Okay, thank you. About the epsilon greedy. For epsilon greedy, it works based on a variable which is called epsilon. The amount of epsilon is a value between 0 and 1. We cannot define a specific value for the epsilon, because for each scenario, the different epsilon value can be better. For example, for my scenario, 0.1 can be the best value and will get a best result for me. But when it's come to other scenario, the other value of epsilon can be the best value for epsilon. But how it works? After selecting one value for epsilon, for example, 0.2 value for epsilon is selected. With probability of 20%, I will explore the other action, which I'm not sure about this one, they are a best action or not. But with 80% probability, I will select the action which I have a little experience about that action, and until now that action returned the best reward for me. But these epsilon greedy approaches have main drawbacks. It will explore the other noun-based action, or for example, the other slot with the same probability, while sometimes some of them can be also the good action, but the epsilon greedy approach won't explore them properly. For removing this uncertainty, we use upper confidence bound. What is upper confidence bound? Upper confidence bound, at first it will calculate a UCP for each of these slot or each of these actions, and then pull an arm which has the highest value in terms of UCP. It means it will give a chance to other noun-based action to be try more and remove uncertainty. When it's come to Thomson sampling also work the same like upper confidence bound to remove the uncertainty, but it designed based on the probability, the distribution probability. It means it will start from the prior distribution, and during the training, it will try to find the true distribution of the action, of the reward which is returned from each action. Now I will talk about my research, and I will show the simulation result which we did for one part of our research. In this part of our research, we focus to improve the interference which is generated by drones on ground networks. For improving this one, we combine two technologies, the NOMA and multi-arm bandit. I already explained about the NOMA and how it works, but I already explained about multi-arm bandit and how it works, but about the NOMA, which is a stand for noun orthogonal multiple access, I will explain them in the next slide. NOMA is a great technique. It's defined as a great technique in 5G cellular networks to manage the mutual interference between users. For example, here, as we can see in these figures, we have two users, user 1 and user 2. User 1 is closer to the base station, and its distance also is less than user 2. When it's going to communicate and send the signal to the base station, its signal will experience less attenuation. As a result, its channel has a better quality. But in terms of the in terms of user 2, it has more distance. When it's going to send its signal will experience more attenuation. As a result, the user 2 is considered as a weaker user and user 1 is considered as a strong user. Here, in order to manage interference, we have to allocate the power to user 1 and user 2 because the signal of user 1 dominated on the signal of user 2, and it will create a big interference for the signal of user 2. And sometimes if the effect of interference is too much, then the received signal in the base station for user 2 is not detectable. But how NOMA works on power optimization. It means how we should allocate the power to user 1 and user 2, while the minimum requirement of the both user, here it can be the data rate, has to be met during their communication. Here, in order to solve this problem, for UAVs, because they are flying in different location, in each location they have different channel condition, with the power optimization has to be done dynamically. For example, when it's located in location one transmission For example, one value can be the best value for UAV, but when it's flying and moving to the next location, this transmission power is not suitable for UAV, and we have to allocate the other transmission power to UAV. And this process is continue until the end of the flight time of the UAV, and this process has to be done dynamically. For this one, as I said, I combined two algorithms: machine learning, multi-arm bandit, and also noun-orthogonal multiple access. Noun-orthogonal multiple access to allocate the power to each of location of the UAVs, and also the multi-arm bandit for training the agent, which here is the base station, to find the best transmission power for UAV based on its location. After simulating this scenario through the MATLAB, we got some result. And if Pravallika, if you can show me the result, I would be appreciated. We find this result, for example, in this figure, show the result for three approaches, which I explained for epsilon greedy, upper confidence bound, and also Thompson sampling. And as we can see, three of these approaches select the one transmission. We simulate this one just only for one location of the UAV. As we can see, three of these approaches select just only one power. It means this power is the best power for that location of UAV, because after removing the uncertainty for the epsilon greedy, the upper confidence UCP or upper confidence band and Thompson sampling also return the same result like epsilon greedy for us. And for the next slide also, we evaluate the amount of regret which is returned by each of these algorithms. And as we can see here, the Thompson sampling and UCP works better than epsilon greedy, because they remove the uncertainty for each of these action. And also in the first picture, it shows the amount of regret by epsilon greedy. By increasing the epsilon, as we can see, the regret is also increasing, because when the epsilon is increasing, the number of times which we try the noun-based action is increasing. As a result, it's the value of the regret which is returned by this action is returned by this algorithm is also increasing. This is one part of my research which I presented here. If you have any question, I would be appreciated to answer you at the end of presentation. Thank you very much.
Thank you, Fatemeh. As we are already running out of time, I will just quickly give you about my research problem. So my main focus here was to provide better connectivity to the drones which are flying in the higher altitudes between more than 300 meters height. So when the drone is flying in the higher altitudes, there won't be a proper connectivity from the ground base station to the drone because of the distance increased between them, and also the traditional base stations are designed to provide service to the ground users, cellular communication. So that's why we are having some challenges when we are integrating drones into cellular communication. So here for that I have considered tethered aerial base station to provide service to the ground UAVs which are drones which are flying in the high altitude. And tethered base station is a base station which has power supply and core network like a traditional base station which is connected to the ground station, and it is connected to the ground station through a tether wire, which is a power and data cable. So by using a tethered base station, we can place the tether base station in any rooftop building or any remote area where they need proper connectivity to the drones which are flying in the higher altitudes. And using the location optimization of the tether base station, we can provide proper connectivity to the multiple drones at a time. So as the drone cannot learn its own location optimality and it can randomly choose the location, here here I have considered the reinforcement learning approaches to learn the location of the drone of the tethered base station, so that it can choose the perfect location to every time when the multiple drones are flying in the higher altitudes. For that, I have considered 5G communication between the tethered base stations and the drone. And I have considered RL methods such as upper confidence bound and Thompson sampling. And in my research problem, I have seen that Thompson sampling is giving better results with less regret and providing better connectivity to the higher altitude drones. To summarize, we have given introduction of 5G and beyond key capabilities and use case scenarios of 5G, and also the advantage of drones. And we have explained the integration of drones in 5G and also the research challenges in drone communication and the possible solutions using the AI, in our case, reinforcement learning, different algorithms which we consider to give better results. Thank you for listening. If you have any questions, feel free to ask. Thank you.
Okay, thank you very much, Fatemeh and Pravallika. And we have a few questions in the Q&A, and if anybody has any question, please post your question in the Q&A. So I'll start with the first question. It's about the altitude at which drones can travel. Can you give us some information about that?
Generally, if we don't need any permissions and personal use when we are flying the drones, we can fly the drones up to 120 meters height or like 400 meters. More than that, if we want to fly a drone, we need permissions for that. And will there be any data loss during transmission time? Yes, I mean, that is one of the challenges in the drones in cellular communication, which can be addressed. So.
Okay, thank you. The next question, UAV incorporated in 5G systems can have complex and dynamic environments, which can make it difficult for reinforcement learning algorithms to converge to optimal policies. So that's more maybe a comment.
I think this is a kind of comment. This is not a question.
Yeah. Okay. So the next one, do you think RL would be the best choice?
I think, yes, RL can be the best choice, and it would be even definitely better than the multi-arm banded. Because in multi-arm banded, each state is independent from the other state. There is no any dependency or any connection between the state. So I think agent will not able to learn the feature of the environment properly. And also when it comes to complexity, I think for each state, we have to train agent from the beginning until the end. It will increase also the time complexity when it comes to multi-arm banded. Yes, definitely RL would be better than multi-arm banded.
Thank you. Another challenge that I see here is the reinforcement learning complexity. Reinforcement learning algorithm can be computationally expensive, which can be challenging for UAV incorporated 5G systems where resources are limited. This can make it difficult to implement RL algorithms in real-time systems. So that's a comment, or I don't know if you want to add anything to that.
That's a comment, but I agree. I mean, the point he's mentioning is right. Like when for the hardware implementations or anything, reinforcement learning algorithms are a little complicated compared to the machine learning algorithms. But we consider RL here because the main thing is the data. if we have a proper data, we can consider machine learning approaches. As we don't have any proper data, that's why from software side, how to solve the problem, we consider RL.
Are you enabling mobility in these experiments?
Yes, we can consider also the mobility for our experiments. UAV in nature is mobile, and is not. We cannot consider the UAV as a kind of users with a constant location. We have to consider the mobility for the UAVs, and also when it's come to real scenario, we can also consider the mobility for ground users also.
Okay. The next question is about the availability of the presentation on the Science Café website. It will be made available in a couple of days, I think. Okay. And another technical question, do you see NOMA to be more useful technology compared to OFDM technology for 5G?
I think, yes, NOMA it's more useful than the OFDM, but in terms of NOMA is going to allocate one resource block to several users. But when it's come to OFDM, I think the OFDM is kind of allocating the orthogonal resource block to each user separately. But in NOMA, it will allocate 2 or 3 users. It depends on how many users we have our networks in one resource block. Then here we have mutual interference between users, and we have to optimize the power which for users which are using the same resource block.
Okay. Any strategy for overcoming any limitations due to the drone's limited battery life? I think this question is for you, Pravallika.
Yeah, any strategy on overcoming any limitations due to the drone's limited battery. So in the research problem I have discussed, when a tethered base station is serving the UAVs, the drones, if the tethered base station is a smart agent and it is able to locate properly and serve them properly, that can help in saving the battery life of the drone, because if a drone is a like smart agent and learning, it might consume more battery compared to the normal way of using. So according to, like, if we can use the tabs, this can be reduced.
Okay. Is using a base station as a reinforcement learning agent more practical for AI-based drone communications?
I think, yes, considering the base station as a RL agent in comparison with, for example, the UAV, it would be more practical in the future. Because as we said, UAVs have one main challenges is their limited battery, and if we want to implement a complex algorithm on them, or sometimes a complex scenario during the learning, in terms of energy efficiency, it might not be the optimal, but the base station will not have such kind of problems, and we can easily implement even the more complex scenario on them and even more complex training.
Thank you. Learning processing mentioned during the talk, either UAVs or TUAVs, is assumed to be executed within drones or at the cloud site?
I'm not sure exactly what cloud site mean here, but they are executed within, like, so tethered base stations are, they can be placed in any remote areas, in high rooftop buildings, and drones are generally, like, which are flying in the high altitudes. I'm not exactly clear about this question.
Yeah, I think it's about where is the reinforcement learning will be placed exactly, in the drone or
yes,
base station or anything. And is the mobility supported in MATLAB?
Yes, MATLAB has these features to generate any mobility, even different mobility models, like a random walk, some other scenario also. And also we can generate a trajectory. MATLAB will support these features, yes.
Okay. Next question, as UAV is having limited battery and energy life, how the data can be captured during the horizontal and vertical of the fly zone?
So my research work is mostly for I'm working on the connectivity of drones, and so I'm not exactly clear. I'm not exactly sure to make a statement about this.
This your question also, as UAV is having limited battery and energy lifetime.
Maybe the person who asked the question can add a clarification.
I'm sorry, I'm not clear about that.
Capturing data in terms of horizontally and vertically, it's mean during the flight in terms of energy consumption. Maybe it's his meaning, I'm not sure.
Yeah. You have to type, we cannot activate microphones. Okay, maybe you can try to talk now. Go. Okay, we have something else. I think using AI locally instead of cloud edge, maybe a local edge as a part of the physical layer hardware is a better choice to prevent any privacy and security concerns in practical scenarios. Again, this was a comment.
Yes.
Yeah, Michael,
Yeah.
this is Guru here.
Yeah,
Thanks
nice
for
to meet you,
unmuting
Guru.
me. Thanks, Michael, for giving me opportunity. See, my question is, as this UAV drones travel horizontally and vertically from base station to the from one place to another place and all. So, as UAV batteries flies will have the limited battery life. So the data transmission will happen horizontally and vertically, right? When the time travel is happening, how this will be captured is my question. From one drone to another drone.
You mean air-to-air communication between several drones?
Yes, air to base or base to air, vice versa. How this can be achieved?
So I think if I understand correctly, so basically this is one of the challenges because drones are flying in different altitudes in 3D mobility. So this is one of the challenge to provide proper connectivity to those drones which are flying in different altitudes, not like in 2D, like in certain altitude. So this is one of the challenge to address, like how the data can be like properly transferred. Connectivity perspective, it is one of the challenge to address. So that is the reason even my research work also about like when a drone is flying in different altitudes and how is the connectivity properly happening. So.
Okay, thanks, Pravallika.
Okay.
Got it.
And we have one last comment. I think BS can act as a guidance in supporting drone-to-drone communications at multiple altitudes. Okay, I think we're done with the questions. I don't say anything else. So I would like to thank the speakers, Fatemeh and Pravallika, and also all the members of the audience for joining us this afternoon. Thank you very much and have a nice day.
Thank you very much, everyone, and have a nice day.